morning, sir. So, good evening, sir. Good evening. Can we start the session?
Yes, ma'am.
Okay. So, Monir, do you have any doubt regarding the week 6 lectures?
Actually, madam, I am out of station, tha. So I can't attend the lecture.
Okay, okay. So, did you attended the assignment 6?
नहीं मैडम, आज
So,
करने वाला हूँ ऐसा है, क्योंकि मैं आज अभी शाम को ही आया 5 बजे ऐसा है.
okay, means you didn't attended the lecture and assignment both.
Yes, madam.
Okay. So, is my screen visible?
Yes, madam.
Okay. Okay, then I will start giving the overview of the week 6 lectures.
Oh,
So, in week 5 lectures, we studied about uh, the annealing process. So, annealing process, three types of mechanisms are there. First is recovery, second is recrystallization, and third is grain growth. So recovery is the uh, uh, means release of strain energy by rearrangement of dislocation like polygonization and formation of low angle grain boundaries and with polygonization. Recrystallization is the formation of strain free grains. We studied the up to recrystallization in the week 5 lectures. So we will start with the grain growth now in this lecture. So grain growth is what like if recrystallization, if the sample is if the sample is about to was kept on the same the annealing temperature, so grains will start to grow. So in the microstructure, if we see, like some grains are this shape, some are small, so some can be of 4 sides, some can be of 5, some can be 6, and more than the so these are the edges of the grains. So if the so according to the rule, if the edges of the grains is less than 6, then those grains will shrink, and the grains which have greater than which have the edges greater than 6 will grow. So so the grain growth happens due to the grain boundary migration. Means if there is one grain, if there is another grain, so it will start growing in this direction or in this direction. So this depends on the curvature of the grain boundary also. So grain boundary migration occurs so that it can consume rest of the strained grains. So once in the recrystallization process, the strain free grains form and they start growing, and so that strain free nucleus starts to consume the rest of the material which will strain free which will get the strain free. So the grain growth mechanism we can see by the example of soap bubble growth. Like in soap bubble also we see like some bubbles grow at the expense of consuming the small grains. Just wait. Sorry for the interruption. So in the soap bubble also we see that some bubbles grow with the expense of small bubbles. So the grain growth is similar to that. Unable to. Yeah, sorry for the interruption. So the grain growth we can suppose like the soap bubble growth also we see that some bubbles expand by the consumption of small bubbles. So grains with less than 6 side uh, appears like this. So first they have the this curved boundaries, means concave from the inside. So they move inwards, and grains along beside them uh, will will grow will grow at the same time. So the green boundaries shrink to the means green boundary migrates inward to move this, and after that, with progress of green growth, they comes to the triangle shape also will have the curved boundaries that will move inwards, and ultimately they disappear, and the grains the neighboring grains grow at the same time. So the angle between this is the maintained as the 120 degree, because this curvature tends to move center and ultimately disappear. And if the grains of more than 6 sides are of this type, means in less than 6 sides they are curved outward, and in the grains of edges more than 6 the boundaries are curved inside, so they start growing outward, and that's why they this is how they grow outward. So the grain growth means some grains collapse or some grains grow is called the geometric coalescence, can also be called as the geometric coalescence. Geometrical coalescence. So like if we see two grains are there, A, and some small grain is here, so this is C. So C, for the during the growth of A and B, the C grain has to shrink. So the boundaries between A and B will disappear after some time. Like it will form like this, A and sorry, I will make it here. So A, this will be B. So C is consumed by the A and B, and there will be no boundary between the A and B grains, and C disappeared in the grain growth mechanism. So this boundary forms, sorry, so the final grain boundary is called as the grain boundary, which has the high angle. Means initial grain, this is C. So the boundaries of the C grain can be of low grain boundaries, and because of the further recrystallization temperature, the the grain boundary rotate, and uh, they make the high angle grain boundaries between the two grains. So these are called as the high angle grain boundaries, which has the misorientation greater than 15 degree. So low angle grain boundaries has the misorientation less than 15 degree. Recrystallization. So, so due to the high angle grain boundary, means the misorientation is high, so the energy of this boundary is also high. So after some time, this boundary also will disappear, and the A and B will be single grain. So this will A and B will will be single grain after some time during
Madam, a doubt here.
yes.
For high angle, energy is high, and for low angle, energy will be low.
Yeah.
Okay, madam.
So so if we make a graph between recrystallized grain size and the percent deformation. So the curve of this will look like this. Like with increasing the percent deformation means if cold work is higher, then the recrystallized grain size will be fine. And this uh, the minimum amount of deformation required for the recrystallization is called as the critical amount of cold work. Means for the recrystallization we need some cold work in the material. So this is so up to this point the recrystallization is primary recrystallization. Means this includes the nucleation and growth. The grain growth after recrystallization, which is also so in the when nucleation and growth of strain-free grains are done, so the secondary recrystallization process starts. In secondary recrystallization, the grains grow up more than the extent of more than the required grain size. That that can be called as the abnormal grain growth. So this abnormal grain growth also not required for the mechanical properties, because the some grains become very much big, and some grains will shrink too. So the uh, distribution of grains will also be asymmetric in the abnormal grain growth, and this will hamper the mechanical properties. So due to the abnormal grain growth, mechanical properties will be low. So to uh, to avoid the abnormal grain growth, the recrystallization time and temperature plays a role. Means if temperature is high and if we keep the material for a very long time, then the abnormal grain growth happens. And the recrystallization time can be fixed, but the temperature is not fixed, not a fixed temperature. So both we can say that the both are not a fixed variable. Means time and temperature can vary. If temperature is high, then time will required for the recrystallization will be low, and if time is high, then temperature required for the recrystallization uh, will be low. So the temperature at which a particular metal with a particular amount of cold work will recrystallize is called the recrystallization temperature. That is the definition of recrystallization temperature. So if we see uh, uh, through a graph, so this is the percent recrystallization. So if we see along the log of time, so let's say if this curve is for some temperature T3, this curve will be for the another temperature, and this curve will be for another temperature. So here in this curve, the T3 is greater than T2 and T2 is greater than T1. So for the T1 temperature, means the lowest temperature, the time for recrystallization will be high, like we see. For a 50%, if we draw a line at the 50% recrystallization process, so for the higher temperature, the time will be low. For the low temperature, the time for recrystallization, 50% recrystallization is higher. T1, T2 and T3. So this is time and this is temperature. And if we plot another graph, which is the 1 by reciprocal of 1 by absolute temperature, and this temperature is the recrystallization temperature, and here is the time for 50% recrystallization T. So the we get a straight line with the slope of, so the slope of this curve will be 1 by T equals to K log T plus C. So the intercept will be K, and this intercept will be K. So this is slope. So equation of this line can be written as the 1 by T equals to K log of time plus intercept. So for this 50% recrystallization, the kinetic equation can be written as the 1 by T equals to A e raised power minus Q by RT. So here T is the time and T is the recrystallization temperature. So here Q is a constant. Q is the activation energy for recrystallization. R is gas constant. So uh, this case, so the case we studied is the annealing process, but so the recrystallization is the uh, in the annealing process, but the recrystallization process can also happen at the during the deformation. If that deformation is performed at a higher temperature, means hot deformation, if there is hot deformation of a material, then recrystallization can also happen during the deformation. That is called the dynamic recrystallization.
मैडम once again repeat करना.
हाँ. So the recrystallization,
Dynamic
yeah,
recrystallization.
dynamic recrystallization is that the means we before that, before this, इसके पहले जो हमने पढ़ा था वो recrystallization था during the annealing process. Means we deform the material first, then we anneal it, then recovery, recrystallization and grain growth process happens. But the recrystallization can also happen during the hot deformation, like if the deformation is performed at a higher temperature. So in the processing, we generally use high temperature to easily deform the material. So during the hot deformation, the recrystallization process also happen during this, because of the once is one in this method, sorry, in this in the hot deformation, we have the cold work, means percent deformation is there, and uh, hot means there is temperature also. So due to the combination of high temperature and percent cold work, recrystallization process also happens during the deformation process. That's why it's called the dynamic recrystallization. Means recrystallization is happening during the deformation. Understood?
Yes, ma'am. Thank you.
Sorry. So the dynamic crystallization is again classified into three types. Like it is dynamic crystallization can be written as the DRX, and it is classified into three types. First is the discontinuous dynamic recrystallization. Second is the continuous dynamic recrystallization, and third is the geometric recrystallization, dynamic recrystallization. So the all three types of dynamic recrystallization differ each other because of the mechanism during the recrystallization process. So first we will start with the discontinuous dynamic recrystallization. And one more thing, that this all three types of dynamic recrystallization depends on the material properties, like the stacking fault energy of the material. So the first we'll start with the discontinuous dynamic recrystallization. So discontinuous dynamic recrystallization happens in the material which has the low stacking fault energy. Low stacking fault energy we studied in the previous lectures, like if the dislocation dissociate into two partials, so the energy created due to the partial is called the stacking fault energy, which is related to the inversely proportional to the width between these two partials. So if the width between two partials is less, stacking d is less, then stacking fault energy will be high, and if d is the separation between two partial is high, then stacking fault energy will be low. So in the low stacking fault energy materials, the discontinuous dynamic recrystallization occur. So in this process, DDR, this is also called as DDRX. So the DDRX process happens first the first this recrystallization occur due to the nucleation of strain-free grains during the deformation. And the strain gradient between the dislocation. Sorry, between grains. So what is the strain gradient difference in the grains? So we can see that the different grains can have the different dislocation density. In that means if this one or two grains have the this has the more dislocation density, and this has the less dislocation density. So the dislocation density uh, contribute to the strain energy of this grain and this grain also. So with the high dislocation density, the strain will be higher in this grain, and strain in the second grain will be low. So due to the difference in strain, the strain gradient exists between two grains. So due to the strain gradient between these grains, uh, the dislocation accumulation happens in the DDRX process. One more thing is that the low stacking fault energy means in low stacking fault energy material, the dislocations cannot cross link. Easier and accumulation of dislocations happen at the grain boundaries. So for that, as we see that the some critical coal work is required for the recrystallization. So here in this process also some critical strain is required for strain gradient to uh, exist between the two grains. So critical strain is required. So the grain growth first is the nucleation of strain free region, then the strain free region uh, grow by the grain boundary bulging method. And serrations are also formed due to the accumulation of dislocation in this process. Serrations are the uh, serration can be related as the deformation bands. Means localized deformation. Formed in green boundaries. Serration formed in green boundaries, so that lead to the bulging of the green boundary due to these serrations. Green boundary bulge. So flow behavior. So the deformation during the process depends on the time. Sorry, this is temperature of the deformation, strain rate, and one more factor comes in the dynamic recrystallization is the Zener-Holloman parameter, which is written as the Z. So Z can be written as strain rate multiplied by exponential of Q by RT. So here E dot is the strain rate, Q is the activation energy, R is gas constant, and T is the temperature. So due to the grain boundary bulging, subgrains are formed with the continued deformation process. So in the subgrains formation due to grain boundary bulging. And these subgrains are also formed are also surrounded by some type of boundaries. Means how the subgrains are formed. If subgrains are formed because of the formation of the twin boundary, for subgreen boundaries. So the if the hollow the this the time and strain rate and the Zener Hall parameter, if the value of the Zener Holloman parameter is high, so for high z value, high strain means the high z how it will be. So if strain rate is high and temperature will be low, then this parameter will be uh, the value of this parameter will be high. So for the high z value means high strain rate and the lower temperature, so uh, subgrain boundaries present in this case. And for low z means strain rate is low and temperature is high. In the high z condition, strain rate is high and temperature is low. So the in the low z condition, twin boundaries surrounds the subgrain. So how we will see the mechanism that how the grain boundary bulging happens. So if this is a grain, so this grain boundary will start to migrate along this direction. So migration start, then the sorry in the second process, the this curvature will start to increase and form the bulge like this. So the Zener-Holloman parameter decides the grain boundary surrounding. So Z is the boundary deciding. So as this boundary bulges out, the serration is formed near the near the bulges, means localized due to so the boundaries will start to develop. And the second process, this is the development of boundaries along the subgrain, means this is the subgrain and some boundaries are also start to form near these boundaries. So they that are called the subgrain boundaries or twin boundaries. So the subgrain boundary, twin boundary depend on the Zener-Holloman parameter. So how the this subgrain and twin boundary forms, so this is the dislocation, because the dislocation density differs in the subgrain boundary and twin boundary. So due to the accumulation of dislocation near these grains, the dislocation density gradient also generate near these boundaries. Near grains. So the dislocation density gradient is the driving force for the formation for the grain boundary bulging to occur. So the final formation will be of this type, means these are the serrations, means the deformation bands form near the subgrains. So the serration formed near the subgrains are called the subgrain boundaries, and if twin forms near the subgrains, then twin boundary will be there. So the formation of this subgrain boundary is due to the rearrangement of dislocations. Means dislocation rearrange at this position, means near the subgrains. So at low strain rate, if the strain is low, grain boundary sliding can also happen. happen. So at low strain, grain boundary sliding happens, means at low strain grain boundary sliding is more prevalent. Due to the grain boundary sliding, serrations will dominate in this condition, means to further and give these serrations giving rise to further strain gradient between the two grains, and increasing the driving force for the recrystallization. So if we see that one, so these are the grain boundary shearing. So some regions are formed at low strain. Yeah, so this is the mechanism happening during the discontinuous dynamic recrystallization. So first is the at low strain grain boundary sliding happens, that will lead to serrations near the boundaries. Second is the so this is the mechanism of the grain boundary sliding. Like, so due to the plastic deformation, some regions are created at this boundary that lead to bulging out of this part of the of grain boundary. So this reason lead to the like that will start bulging out like this. Initial shape was this, and the final they will start moving out. So this means bulge formation. For these grains also the bulge start to form and grow outward. So in these two grains we can distinguish how subgrain boundaries are formed. So subgrain boundaries are formed due to the serrations present near the grain boundaries, and if the boundary is like looking like this, then this is called the twin boundary. This is formed for uh, low z values. For high z value, these are the subgrain boundaries. So the strain energy gradient exists, that is present during the this deformation process is written as the delta E equals to K K1 gamma B by L, where delta is the strain energy difference per unit volume across the boundary, means across this the strain energy difference, which is per unit volume. Across the boundary. Gamma B is the boundary energy per unit area. Means the surface energy of this boundary will written as the gamma B. Delta is the strain energy difference between here and here, and L is the boundary length before bulging. Because means the initial length, this. So this is the dynamic recrystallization process which happens in the low stacking fault material. Second is the continuous dynamic recrystallization. So up to this point, do you have any doubt?
No, madam.
Okay. So next is the continuous dynamic recrystallization. So the continuous dynamic recrystallization means the uniform recrystallization process is uniform across the material. Uniform across the part. So how the CDR is, this can also be written as the CDRX, and first was the DDRX. So in the DDRX, first is the nucleation of strain free grains, nucleation, and a grain boundary bulging due to a strain gradient. While in CDRX, which is continuous dynamic recrystallization, involves a progressive transformation of dislocation. This is the progressive transformation of dislocation subboundaries. That leading to formation of strain free grains. So, what is the dislocation sub boundaries? And the CDRX also happens in the high stacking fault energy material. So, in the high stacking fault energy material, the dislocation are able to cross slip. Can cross slip easily. That will lead to different arrangements of the dislocations. When during the deformation, dislocation density increases, and those dislocation cross slips and form the sub boundaries in the in a single grain. Means this is a single grain, so the dislocation arrange in some manner and form this type of regions. So these regions and the boundaries of these are called the dislocation sub boundaries. So due to cross slip, the dislocations can easily rearrange in different type in different patterns and form dislocation into the and here the form and the if this rearrangement leads to low energy grain boundary. Means after the subgrain boundaries, those subgrain boundaries, dislocation sub boundaries transforms into the low energy grain boundary. NAGB. So what is the mechanism of the CDRX? Like if we see a part which is deformed, like this, here we can see so this is the initial part which is deformed for the low up to low strain. So these dots are shown because of to measure the formation of formation of the strain free nucleus. Means so the strain free nucleus are formed throughout the part during the deformation. So this is cold worked material. After further deformation, the thickness of the part will decrease, and in this part, like the boundaries also comes means green boundaries also come near to each other, and in the boundaries small the nuclei grow and form the uh, small boundaries, small grains inside the initially deformed grains. So in the previously deformed grains, small strain-free grains are nucleated. So this process is after the heating, means is called deformed by heating and deformation. Further deformation, the strain-free grains form, and after some point where lattice motion. So after this point of heating, the form the newly formed grains transformed into high angle grain boundaries by the lattice rotation. Means if we sorry,
um, one doubt here.
yeah,
uh, ड्यूरिंग हीटिंग प्रोसेस जो फर्स्ट हम कोल्ड वर्क करते हैं उसके बाद हम रिक्रिस्टलाइजेशन स्टार्ट करते हैं हीटिंग.
yes, huh. So
ओके मैडम.
means in this process, this is dynamic recrystallization. So we are showing the difference between cold working and this is heating, means the hot deformation.
मैडम मेरा क्वेश्चन ये है कि जो हमारा जो कंपोनेंट है या वर्क पीस है वो इनिशियल स्टेज में प्री हीटेड होता है या नहीं है प्री हीटेड.
नहीं, preheated, that depends on the process, means what we want to. In cold working we don't preheat the material, but for the hot working we use the preheating.
ओके मैडम.
Okay. And preheating can also be say as the, means the heating during the deformation, means some heat is provided during the deformation process.
ओके मैडम.
Okay. So after some point, and just wait. So some grains are formed like this. So the blue grains are formed after the lattice rotation, means the green boundaries after the hot deformation and nucleation of strain free grains. The due to the formation of these dislocation sub boundaries, they will they will rotate and form into this high angle green boundaries. So these first are the low angle green boundaries, and after rotation this is the means the blue grains are formed because of the lattice rotation. And that are called as the strain induced high angle green boundaries. So the low angle green boundaries, which are the dislocation sub boundaries, form into high angle green boundaries by the lattice rotation process. So therefore the progressive transformation happens, means uh, with some time or with the time, the most of the greens that are formed because of the dislocation green boundaries starts rotating and form the high angle green boundaries. So the progressive transformation, this is means with time the all sub dislocation sub green boundaries which are potential which have the potential to rotation transforms into the high angle green boundaries. Progressive transformation and increase in misorientation. And that results into the recrystallized fine grains. So the dynamic recrystallization process is the high temperature process, and deformation should also be high. So the progressive transformation and increase in disorientation results in the recrystallized fine grains. So the how the dislocation rearrangement into the low angle grain boundaries is called the dynamic recovery. So the recovery process during the hot deformation is called as the dynamic recovery, means the formation of low angle grain boundaries due to the rearrangement of dislocation. So as the this migration, the migration of so as the rotation uh, stops, the green serration starts to form in this process also. To form near grain boundaries, means after the uh, rearrangement or dislocation, lattice rotation, and some the serrations started to form with the further deformation process, uh, and the serration are because of the uh, difference in strain energy in two grains. So the serration can also be uh, overcome or ruled out by migration of grain boundaries. Mm, So the mechanism of formation of this is also seen as the serration ruled out because of the migration of grains, and the uh, grain boundary bulging starts. So the process in this is like, if these are the two grains, so the strain region formed near the boundaries leading to serrations, means this is the plastic deformation region near the grain boundary. So by plastic deformation only at the grain boundary occur, because dislocation accumulate at this near the grain boundaries, and they apply force, increasing the stress concentration at this point. So due to the stress concentration, the plastic deformation happens near the grain boundaries, plastic deformation region. So after this point, this bulging of the grain boundary starts, and the serrations formed near the boundaries. That will lead to, so this bulging will continue, and for this is second process. So after this bulging, these new grains are formed, which also create some deformation points near the corners. Means after the formation of the grain boundary bulging and formation of these new grains, deformation region creates around the edges, that results into the rotation. Means this edge rotate to this position, and form like this. This edge will also rotate to this position and form like this. So this is the grain boundary rotation. So here it is the grain boundary bulging, and this is the rotation. Just 1 minute. So during deformation, after the rotation, micro shear bands are formed. So this final position is the subgrain, mm, that are newly formed. So during the deformation process, micro shear bands are also formed with that lead to uh, that also leading to continuous dynamic recrystallization process. So the dislocation substructures formed at a low strain strain due to micro shear bands only. So we'll study the micro shear bands also due to, so the substructures are formed due to the micro shear bands only. And so and the next stage is the increase in misorientation. Yeah, so micro shear bands are same as the, like I explained as in here, like due to plastic deformation region created by the stress concentration, plastic shear bands are formed. These are called the micro shear bands. Means in the dynamic recrystallization we see that the localized deformation happens because of the deformation bands. So the micro shear bands are similar to deformation bands. Means small regions formed near the boundaries. Shear bands. So the micro shear bands leads to the formation of dislocation substructure. Increase misorientation. And further formation of micro shear bands as deformation proceeds or continues. the grain interior. So the further formation of micro shear bands are in the grain itself, in grain interior. That all that further leads to increase in misorientation. Means as we see that in a grain, these are the boxes are the dislocation substructures. If we zoom out the this region, if we can see as the A and B region, then in this region small form shear bands are formed like this. Though, so the structure looks like this if we zoom out this dislocation substructure. So the boundaries, so the blue region is formed because of the high angle grain boundary, and the yeah, black region is the low angle grain boundaries. So the combination of high angle and low angle grain boundaries resulted into the fine recrystallized fine grains. Means in one grain there are sub grains are formed, and in the sub grains the high angle and low grain boundary forms because of the dislocation rearrangement in the grain or sub grain. So this is how the grain size is reduced, is decreased, and grain size is decreased. So the misorientation is so if the misorientation is large enough, means in the process of the formation of sub dislocation subgrain boundaries, then due to the micro shear bands dislocation substructure, means here we see that the first micro shear bands form and that lead to dislocation substructure, that further increase the misorientation, form the micro shear bands again in the grains, and that lead to more high angle and low grain boundaries. So if the misorientation is large enough, uh, equiaged microstructure can be formed, also be formed. Means as the misorientation will be high, so the process of grain refinement will be across the part, all over the part, so that lead to equiaged grain size, grain formation. So the equiaged grain formation can also be formed in the severe plastic deformation process, SPD, which is the means in this case is in the as the deformation is increased very high, means continues to deform the material, so misorientation will be very high. That means that is called as the severe plastic deformation, leading to the equiaged grain formation, means very fine grain size will obtain. So the formation of severe uh, plastic deformation and the micro shear bands and severe plastic deformation depends on the material, temperature, strain, and strength of the material. So these all factors decides the formation of micro shear bands and severe plastic deformation. So we can see that the for example, if in aluminium alloys, aluminium has the high stacking fault energy, means stacking fault energy is very high. So the recrystallization process is also prevalent in the aluminium alloy process, in the aluminium alloys. So next is the geometric dynamic recrystallization. Which is the GDL, written as the GDRX. So GDRX also occur in the high stacking fault material. For GDRX, high stacking fault energy is required, and a critical strain. So what mean by the geometric dynamic recrystallization means in this process the shape of the grain changes after the recrystallization process. For this a critical strain is required. For example, if we take rolling, grains elongate during the process, and that will that allows the formation of geometric dynamic recrystallization grains. So we will see that how the grain shape changes during the rolling process. Means first is the grains are formed. So these grains formed. So in the second process, with deformation, the width decreases, that lead to shrinking of these grain boundaries, and the grain boundaries comes near to each other. This is second process. In the third step, uh, more decrease in width, and the grains comes very near to each other. Means so as the grains comes to each other, there will be like this type of shaking. So these two boundaries impinges to each other and forms a single boundary. Like if there is a single, and form the shape like this. Means they pinches out to each other as the deformation proceeds. So this lead to the shape change of the grains after deformation due to the compressing of the part. The grain boundaries come to each other, and the different grains kings out, form the pinches to the other grains, and form a new shape.
Madam, during this process, strain rate is increasing
No, strain rate
in
is not
step number
increasing.
one.
Strain is increasing.
Oh,
Strain rate is same.
okay,
Strain rate is same. Strain is increasing.
okay, madam.
Means as the deformation proceeds, the more decrease in width will be there, na. So the process is the first is the thinning down of grains. Second is the size of serrations. Means serrations are also formed during the deformation process as the deformation is continued. Becomes comparable to the grain thickness. Means between these grains some serrations also form. So due to the continued deformation, the serrated region increases, and that become comparable to the grain thickness. And the third point, in the third stage, aqueous grains can pin. So the aqueous grains can pinch off as the serrations impinges. Means the between the two grains there are serrations. So due to the serrations present, they comes and form a pinches out, can pinch off. So this is the process of dynamic recrystallization, geometric dynamic recrystallization. So up to this point, uh, we studied the all process of annealing and the recrystallization during the deformation also. So all this process leads to the grain refinement, means decrease in grain size after the uh, after the deformation and annealing process. Means the initial part has the uh, coarse grain size that is deformed, means called worked, and so during the cold work strained grains formed. Those strained grain material uh, subjected to the annealing process or dynamic recrystallization that lead to uh, refined grains. So the refined grains has the low small grain size. So what will happen with the small grain size as compared to the coarse grain material? Means with in decreasing the grain size, strength of the material increases. That's why this process we do, means deforming and annealing process is required to refine the grain size. So how the grain size contributes to the strengthening method. So one is the grain refinement. Next topic is the grain refinement, in which we study the Hall patch relation. So Hall patch relation says as the yield strength is equals to sigma naught plus k by square root of d. So here sigma is the yield strength of the material, sigma naught is the lattice friction stress, where k is the locking parameter and d is the grain size in micron. So here we can see the yield strength of the material is inversely proportional to the square root of grain's diameter. As the grain diameter increases, strength will go down. If grain size decreases, strength will go up. So the grain boundaries acts as the obstacles to, so how the grain refinement leads to strengthening. The grain boundaries, so as the deformation proceeds, the dislocation find difficult to cross the boundaries of grains. Means the grain boundaries are obstacle to dislocation, and they accumulate at the grain boundaries. So if the grain boundary area will be high, the dislocation restriction will be high, and due to the high restriction, the grain strength will go up, means strength will be higher. So that's why with decreasing grain size, grain boundary area will be high, and the strength will increase much higher, will increase to a much higher extent. Means if we can see, like, this is a this is grain boundary. The dislocation accumulate near the grain, so the accumulation length can be written as L, and this can be the dislocation source. From which dislocations are generating. So if the number of dislocation here is n in the pileup, so n can be written as the k pi toy s l L by GB. Here K is a constant, toy S is the average resolved shear stress here. G is shear modulus, and B is Berger vector below, and L is the dislocation pileup length. So if the Berger vector of a dislocation is B, so the Berger vector of a pileup will be a pileup of dislocation, and n dislocation will be NB, and stress generated at the pileup can be written as the NB toy S. So for a dislocation source at the grain center, means this is a dislocation source of and the grain diameter is D. The number of dislocation at pileup can be written as the K pi toy S D by GB. D is the grain diameter. So in the case, the pileup length will also be D. To deform to overcome the pileup of the dislocation, the critical stress, resolved shear stress should be applied. That is can be written as the toy C. So toy C can be written as the n time of toy S, means average shear stress of one dislocation. So for n dislocation, toy C will be n toy S. So if we put the toy s value here, the n value here, toy c will be k pi toy s square d by gb, and toy s can be written as the toy which is applied shear stress minus toy I. Toy I is the lattice resistance to dislocation motion. So this can be written as the toy c k pi toy minus toy I का square d by gb. Four, here it is written as the 4b. So if we rearrange this equation, toy minus toy I square equals to 4 toy c gb by k pi d. So take out the square, toy minus toy I equals to square root of 4 toy c gb k pi d. That lead to toy equals to toy I plus some k k dash divided by square root of d, means this term is written as the k prime and this will be written as the square root of d. If we change the shear stress to principal stress, then this equation can be written as the sigma equals to sigma I plus k dash square root of d. So here k dash is square root of 4 toy c gb by k pi. So that so in this way we can derive the Hall patch relation for a dislocation pileup near the green boundary. So a dislocation pileup create the increase in strength from this uh, from this equation. Yeah, so today lecture content is over. Do you have any doubt?
Yes, madam. One doubt here.
Yeah.
Uh, in a annealing process, there are three steps:
Yeah.
recovery, recrystallization, and deformation.
Grain growth.
Grain growth. Uh, uh, During the annealing process, recrystallization increase or decrease.
Recrystallization depend on the time and temperature uh, that for the material that मतलब अगर कोई पार्ट है उसको हमने कितने टाइम तक और कितने टेम्परेचर तक आफ्टर रिकवरी रखा, तो रिक्रिस्टलाइजेशन डिपेंड्स ऑन दैट टाइम एंड टेम्परेचर आफ्टर रिकवरी.
ओके मैडम, और पार्शियली जो कोई कंपोनेंट है उसे हम पार्शियली रिक्रिस्टलाइज करते हैं, तो जो हमारा ग्रेन ग्रोथ है वो नॉर्मल रहेगा ड्यूरिंग प्रोसेस या आफ्टर प्रोसेस?
अगर हम पार्शल अनिलिंग करते हैं तो
हाँ,
partial in partial annealing, so only the recrystallization is limited to some extent. Then abnormal grain growth उसमें नहीं होगा.
ओके ओके मैडम.
Okay. And means in some part can also be seen that the driving force uh, available for the during the annealing process. So if the recovery is con- consume the more strain energy, then recrystallization will need the high driving force. Means the driving force for recrystallization is higher than the recovery process.
ओके मैडम, इसकी इफेक्ट रिडक्शन इन बाउंड्री एनर्जी आती है ना,
Sorry. हाँ.
ड्राइविंग फोर्स फॉर ग्रेन ग्रोथ,
Yeah.
तो इसकी इफेक्ट हमें जो हमारी जो बाउंड्री एनर्जी है उसमें दिखती है ना, रिडक्शन आता है.
हाँ हाँ.
ओके मैडम.
ओके.
ओके, थैंक यू मैडम.